Hello everyone, and welcome to another lesson. In this section, we're going to move on to a new topic, which is graphing. But before we begin graphing, we're going to look at our practice problems from last time. We will cover them relatively quickly because it is something that you should be comfortable with at this point. But we will go over them just in case there's some things that you are not clear on just yet. So, without further ado, let's begin. Our first problem was the Wemo Lawn Care Service problem. The Wemo Lawn Service wants to start doing snow removal in the winter when there are no lawns to maintain. Jeff and Julie Weems, who own the service, are trying to determine how much equipment they need to purchase based on the various job types they have. They plan to work themselves and hire some local college students on a per-job basis. Based on historical weather data, they estimate there will be 6 major snowfalls next winter. Virtually all customers want their snow removed no more than 2 days after the snow stops falling. Working 10 hours per day, Wemo estimates that they can remove the snow from a normal driveway in 1 hour, and that it will take about 4 hours to remove the snow from a business parking lot. The variable cost, labor and gas, is $12 for a driveway and $47 for a parking lot. Using their lawn care business as a guideline, they believe demand will not be greater than 40 homes and 25 businesses. They plan to charge $35 for a home driveway and $120 for a business parking lot. They want to know how many jobs of each type they should pursue in order to maximize profit. So, we've got the basic information here. The first step, as always, is highlighting our decision variables. To do that, we look at what is being chosen. In this situation, they're choosing how many jobs of each type they should pursue to maximize profit. So our decision variables become X1 is home jobs, X2 is business jobs. The next step is highlighting the relationship that connects our ultimate goal with our decision variables. In this situation, our ultimate goal is maximizing profit. Usually, not always, but usually, we can find this information in the last sentence of our problem. Moving on, we know we're trying to maximize profit, so to do that, we have to look over here and connect our profit maximization with our jobs. We see it's $35 for a home driveway and $120 for a parking lot driveway. However, that is revenue, not profit. In this question, the curveball they threw at you was asking you to find profit based on revenue and cost. To find profit, we subtract cost from revenue. So we see here that we have both our costs and our revenue. Costs were $12 for a driveway. Revenue is $35 for a driveway. Cost is $47 for a parking lot and $120 for a parking lot in revenue. So our objective function becomes not 35x1 plus 120x2, but our objective function becomes 23x1 plus 73x2. Now we have our objective function. We have to look at our constraints in this situation. So constraint number 1. We see there are 6 major snowfalls. We cannot work the day of the snowfall because we can't guarantee to remove all the snow. So we have to start the day after. However, We also know we have only 2 days after to remove that fallen snow. In that scenario, we're in a situation where we have to understand that our times are different. We have 12 days total, 6 snowfalls, 2 days after each snowfall, and we're working, as we see here, 10 hours per day. So what we can do 2 things. We can convert all of our information to hours. 12 days times 10 hours is 120 hours. Or we can convert our information into 10-hour days. So we see a normal driveway takes 1 hour and 4 hours for a business parking lot. We can do this 2 ways. If we do that in terms of days, 12 days, it becomes 0.1 of a day, 1 divided by 10, and 0.4 of a day, 4 divided by 10. And we have 12 days total. We can see that here. 0.1x1 plus 0.4x2 is less than or equal to 12. We can also do it a second way. We can convert this to hours, as I said. 12 days times 10 hours is 120 hours. And we have 1 hour and 4 hours. So in that situation, we have a second alternate constraint. Not a new constraint, but an alternate. And we see it's 1x1 plus 4x2, and it's less than or equal to 120. This is our first constraint. Our second constraint, we go back and we see that it is demand will not be greater than 40 homes. So x1 is our number of homes we choose, and x1 cannot be more than 40. So very simply, we come over here and we make x1 less than or equal to 40. Again, demand will not be greater than 25 businesses. So we come down here and we make x2 less than or equal to 25. So in that situation, we see that we have 3 constraints and an objective function that takes into account both revenue and costs. So once we have this information, we collect it all in one place like we do here. And we see our final problem formulation, max z equals 23x1 plus 73x2. Or in natural language, we're trying to maximize profit. If we receive $23 in profit per home driveway and $73 per profit for a business parking lot. However, we are subject to 0.1x1 plus 0.4x2 less than or equal to 12, which means 10% of our day for a home parking lot plus 40% of a day for a home parking lot, a business parking lot, and we have less than or equal to 12 days to work. We also know that x1 is less than or equal to 40, meaning demand for homes will be less than or equal to 40, and x2 is less than or equal to 25, meaning demand will be less than or equal to, our business parking lots will be less than or equal to 25. So, collecting this information in one place here, we would then be able to solve this equation and determine our optimal choices. In this situation, our optimal choices are based on determining the perfect number of driveways to clean and the perfect number of business parking lots to clean to maximize our profit if we receive this much profit per home and this much profit per business parking lot. If you are unclear on this solution, please contact me through Kakao, because as of today, we're going to move into solving these problems. If this is difficult for you, It will only get harder as we proceed. So, moving on, let's look at the next problem. This is student practice problem 4. Universal claims processes insurance claims for large national insurance companies. Most claim processing is done by a large pool of computer operators, some of whom are permanent and some of whom are temporary. On average, a permanent employee can process 16 claims per day, and a temporary worker can process 12 claims per day. The company receives an average of 450 claims per day. The company also has 40 computer workstations. A permanent operator generates about 0.5 claims with an error each day. A temporary worker averages about 1.4 mistakes per day. The company wants to limit the number of mistakes to 25 per day. A permanent operator is paid $64 per day, and a temporary operator is paid $42 per day. The company wants to determine the number of permanent and temporary operators to hire in order to minimize costs. So as always, we begin by highlighting the key information. This first section is background information and not relevant to our mathematical solution. On average, a permanent employee can process 16 claims per day. Temporary worker processes 12 claims per day. They have 450 claims per day. That will be relevant because that's going to guide or limit our choices. The company also has 40 computer workstations. This is relevant because they are computer operators. If they don't have workstations, it will be difficult for them to operate effectively. A permanent operator generates about 0.5 claims with an error each day. A temporary worker averages about 1.4 mistakes per day. The company wants to limit the number of mistakes to 25 per day. So in this situation, we know again, this is going to guide our decision-making process. Anytime something guides our decision-making process, it's a situation that operates as a constraint in this scenario. Finally, a permanent operator is paid $64 per day. A temporary operator is paid $42 per day. The company wants to determine the number of permanent and temporary operators to hire to minimize costs. So, our decision variables we can find in the very last sentence. The number of permanent and temporary operators to hire. So our decision variables become permanent employees to hire, temporary employees to hire. The objective function involves relating the number of permanent employees and the number of temporary employees to our ultimate goal, which is minimizing costs. The cost of a permanent employee is $64 per day. The cost of a temporary employee is $42 per day. So up here we see, right here we see, we're trying to minimize our cost at $64x1 and $42x2, which is the cost per temporary and permanent employee. In the last section, we begin looking at our constraints. The first one, we see a permanent employee can process 16 claims. Temporary can process 12 claims. We need to reach 450 claims. So the number of claims processed by the number of permanent employees plus the number of claims processed by temporary employees plus the number of temporary employees must be greater than or equal to 450. 16 times the permanent plus 12 times the temporary must be greater than or equal to 450. for our second constraint, we see that we have 40 computer workstations. And we also see that they are computer operators, so every employee requires a workstation, meaning we have a maximum of 40 employees allowed. So we have X1, which is the number of permanent employees, plus X2, the number of temporary employees, must be less than or equal to 40, because that is the number of workstations available. Finally, a permanent employee generates 0.5 claims with an error each day. A temporary worker averages 1.4 mistakes per day. The company wants to limit the number of mistakes to 25 per day. What this means is we have another situation where it's 0.5 times the number of permanent employees plus 1.4 times the number of temporary employees, and that must equal less than or equal to 25. And we can see that here, which is the number of mistakes permissible daily. So we see in this situation, we now collect all our information in one universal place and write it in our universal format. And we get min z equals 64x1 plus 42x2, subject to 16x1 plus 12x2 greater than or equal to 450. x1 plus x2 is less than or equal to 40. And 0.5x1 plus 1.4x2 is less than or equal to 25. Let's briefly discuss what this means. We're trying to minimize our costs. If it costs $64 for a permanent employee and $42 for a temporary employee. But we're governed by 3 rules. The first one is that we have 16 claims for every permanent employee and 12 claims for every temporary, and we have to reach 450. Now, it seems to me like we would quite simply choose permanent employees because they process more. But we know they're more expensive, and we're trying to minimize costs. So we can't choose only permanent employees. In the second one, we have x1 plus x2 is less than or equal to 40. And this means that every permanent and every temporary employee has to have a workstation, and we only have 40 workstations available. So again, we probably want to give our workstations to our more efficient employees because they're limited. But we know permanent are more expensive, so we can't hire only permanent employees. Finally, we have 0.5 mistakes per permanent employee, and we have 1.4 mistakes per temporary employee. In that situation, we know that temporary employees make almost 3 times as many mistakes. So probably we don't want to hire any of them, but they are much cheaper. So what we are ultimately doing, we know permanent employees are more effective. We know that. We know they're the better choice. However, we also know that they are much more expensive. So what we need to do is we need to find the optimal choice where we are meeting all of our requirements, but also minimizing our permanent employees. Because ideally, we want only temporary employees. They're much cheaper. But in reality, that won't allow us to meet all of our requirements, minimal mistakes and minimal claims processed. So in that situation, we know we're going to need permanent employees, but we don't know how many. That's what we're looking for here. We're attempting to determine how many permanent employees give us our ideal solution. So, to do that, we have to solve the problem. When we solve problems, we do it in two different ways. We can solve graphically, at least at the beginning level, and we can solve algebraically. Algebraic solutions we're going to get into in the future. Not yet. First, today, beginning today, we're going to solve problems graphically. So let's move on to that now. So after we've translated the natural language problem into the standard mathematical format, we move to the next stage, which is solving graphically. This we will examine below. To do that, we're going to look at an actual problem. This is the Beaver Creek pottery example. It is an example we've seen before. It's an example we've seen many times. And it should be relatively easy. That's why we're doing it. Because we're not focused on the problem formulation as much as we're focused on the next stage, which is graphing. So, without further ado, let's begin. Quick review, the Beaver Creek Pottery Company is a small crafts company operation run by a Native American tribal council. The company employs skilled artisans to produce clay bowls and mugs with authentic Native American designs and colors. The two primary resources used by the company are special pottery clay and skilled labor. Given these limited resources, the company desires to know how many bowls and mugs to produce each day in order to maximize profit. Does it have the necessary ingredients? We know it does. We highlight those key points here. We know it's clay bowls and mugs. We know their resources are special pottery clay and skilled labor. And we know that we're trying to determine how many bowls and mugs to produce each day in order to maximize profit. Now, we have to highlight the decision variables. That's what we've done here. We know it's a maximization problem, as we've shown here. And we know we have two key limitations, limited clay and limited labor. Now, we've got the key information on the bottom. This information you've seen before, but we will highlight it just so everybody is following along. And we see that X1 is the number of clay bowls that we will manufacture. X2 is the number of mugs that we will manufacture. We're trying to maximize profit, Z, if we receive $40 per bowl and $50 per mug. This information we found following the exact same steps we've followed every single time. And then we write in our constraints. X1 plus 2X2, which is the labor for a bowl and the labor for a mug, with a total of 40 hours of labor available. And 4X1 plus 3X2 is less than or equal to 120. And that's the pounds of clay available. This information here, with 40 hours of labor available and 120 pounds of clay available, was converted into these equations. So we collect all of our information in one spot in our universal problem format right here. And this we have max Z equals 40x1 plus 50x2. Subject to 1x1 plus 2x2 is less than or equal to 40. 4x1 plus 3x2 is less than or equal to 120. From this point, we begin solving the equation graphically. Now, we can solve algebraically, as I highlight here, but because linear programming problems are linear, some problems and solutions at the beginning stages can be solved graphically. These are limited to problems with two decision variables from a practical standpoint. It is possible to solve three decision variable problems because we can graph three-dimensionally, but it is much more difficult once we move beyond 2 dimensions. So realistically, we are limited by having 2 decision variable problems being able to solve graphically. But it is helpful because it allows us to visualize what we are trying to accomplish. The first step to solve visually is drawing a graph. The graph is always drawn the same. The only key point is you have to highlight the horizontal as x1 or your x1 variable and highlight the vertical axis as x2 or your x2 variable. I've done that here. We see that x1 is right here, and that's the number of bowls to produce. x2 is right here, and that is the number of mugs to produce. What this graph represents is every point on this graph. So 10 bowls, 0 mugs. 10 bowls, 10 mugs. 20 bowls, 30 mugs. Each of those points represents a production choice. That is what you're choosing. Those numbers are how many bowls and how many mugs you are going to choose to produce. So, to do this, the next step, once we've drawn our graph, we have to look at our constraint equations right here. 1x1 plus 2x2 is less than or equal to 40. 4x1 plus 3x2 is less than or equal to 20. Each of these constraints will be drawn as a line on the graph. We're going to draw those constraint lines, and that will allow us to find our optimal choices because they guide our choices. So, to begin, we draw our first constraint as a line on the graph. To draw a line, we need 2 key points, and then we connect those 2 points to make the line. So to find 2 points, first, and this is universal, we make x1 equal to 0. And then we repeat, and we make x2 equal to 0. For example, if we make x1 0, 1 times 0 is 0. So this first section is eliminated. And we get 2x2 is equal to 40. We divide x40 by 2, and we get x2 is equal to 20. So if x1 is 0, so we come over here on the x1 axis, and we go to 0 right here, then we know that at 0 bowls we are producing, and we just solved this, 20 mugs. So our first line, our first point on the line is right here at 0, 20. We then repeat the process. For the second constraint, we would do the same thing. We do that, and we make x2 equal to 0. If this becomes 0, x2 is 0, 2 times 0 is 0. x1 is equal to 40. 40 divided by 1 is 40, so x1 is equal to 40. That becomes our second point. So at x2 is 0, right here. x2 is now 0. x1 is 40. So to draw that constraint line, we connect this point and this point by drawing a line right here. This line is now constraint number 1. And this line, because constraint number 1 is labor available, this line represents all production choices where labor is fully used. This line that goes from 0, 20 to 40, 0 is all of the production choices where we're using 100% of our labor. We then repeat that step for the second constraint. And I've done that here. So the first line, the one we just talked about, is here. We see that 1x1 plus 2x2 is equal to 40. We let x1 equal 0, x2 is 20, x2 is 0, x1 is 40. 20, 0, 40, 0. And then we connect these 2 points. That is this line where all labor is fully used. We do it the same for the second constraint. x1 is 0, x2 becomes 120 divided by 3, x2 is 40. We do the same thing again. x2 is 0, x1 is 120 divided by 4, x1 is 30. So we have that as our second line. So x2 is 30, x1 is 40, and x2 is 30. This gives us a point on the graph that will result in the greatest total profit. That's what we're looking for, the production choice that gives us the greatest total profit. So we begin by highlighting the 2 areas that are feasible because we have one resource, but unfeasible because we lack the second resource. We do this by drawing diagonal lines in both areas. So in this section here, we see here that we have enough resources. We have enough clay, but we don't have enough labor. So these choices are impossible. We have enough clay, but not enough labor. Over here, we have enough labor, but not enough clay. So these choices are impossible. Over here, all of these choices are impossible because we don't have enough clay or enough labor. So only in this section here, it is below both lines. So we have both enough clay and enough labor. That's what we see here. So in this section, because we have enough clay and enough labor, these are all of our possible production choices. And these lines represent where all of the choices have been made. We're using all of one resource, all of the other resource, or all of both resources. Now, from here, we highlight the possible optimal points. That's where all of one resource is being used, all of the other resources is being used, or all of both are being used. And that's what I've done here. We've highlighted these 3 areas. Mathematically, we know that our optimal choice is one of these 3 points. No other choice is optimal. Only these are optimal. So we see 20 bowls, 20 mugs, 0 bowls could be our best choice. 30 bowls, 0 mugs could be our best choice. Or it could be a combination of 8 bowls and 24 mugs. 24 bowls, 8 mugs. We don't know yet which one is correct, but these are our 3 possible choices. We have now solved this problem graphically. That is what you're going to do today. You're going to look at 2 problems. And for each of those problems, you are going to highlight possible choices by graphing the constraint lines onto a graph as I've done here. You do not have to submit this, but it will be relevant to your attendance quiz. So, one more time, please watch this video and submit or complete the 2 problems that follow. For the next 2.5 minutes, I will put problem number 1 on the screen. Following that, I will put problem number 2 on the screen. When that is complete, That will be the end of today's video. Please solve those problems, answer the attendance quiz in Google Forms, and I will see you in our next class. Thank you everyone for listening. Here is problem number 1. All right, everyone, here's problem number 2. Both problems are very similar, but the constraint lines will have moved. Good luck completing them. This problem will remain here for several minutes before we end today's video lesson. All right, everyone. So these are the two problems. Neither one has to be submitted, but you will be expected to complete them in order to successfully complete today's attendance quiz. Thank you very much for listening. I'll see you in our next lesson.